Assalamu alaikum. Inshallah, in this video we will start tutorial number 4 about Brayton cycle. This video inshallah will be only about ideal Brayton cycle. Then we will have other videos about actual Brayton cycle and Brayton cycle with regeneration, and we will solve about actual and ideal cycles for both Brayton cycle and Brayton cycle with regeneration under constant specific heat assumption and variable specific heat assumption. Okay, so this video is only about ideal Brayton cycle. In this question, we have an aircraft engine, and usually this one of the applications of Brayton cycle in aircraft engine operates on a simple ideal Brayton cycle. So we have ideal cycle. Okay. So we have ideal Brayton cycle with a pressure ratio of 10. So what is ideal Brayton cycle? Here is the PV and TS diagram for ideal Brayton cycle. Ideal Brayton cycle, the special thing about ideal Brayton cycle is that it operates between two pressure limits. P2 equal to P3, that is the maximum pressure in the cycle, and P1 equal to P4, that is the minimum pressure in the cycle. Okay, the ratio between the maximum limit of the pressure and the minimum limit, the minimum pressure, is the pressure ratio RB. It is equal to P2 over P1, and it is equal also P3 over P4. Okay, so we have a pressure ratio RB is equal to 10. Heat is added to the cycle, so we have heat addition, and heat addition is from state 2 to 3 in this process. We have a heat addition process under constant pressure. Okay, we have two constant pressure heat addition and constant pressure heat ejection process. Okay, so heat is added to the cycle at a rate of 500 kilowatts, so it is a rate, so dot q dot, and it is q dot n because it is added to the cycle and is equal to 500 kilowatt. Okay, air passes through the engine. Okay, we have air because we applied the air standard assumption that the cycle or the working fluid inside the cycle is only air. Okay, for the actual cycle, for the gas turbine cycle, it is other name for Brayton cycle. The gas turbine cycle contains turbine which produces the work. We got fresh air and from outside, and it will go to the compressor. The compressor will increase the pressure and the temperature, and will go to the combustion chamber where the fuel is added. And then when you have a hot air, because when you increase the pressure, also you are increasing the temperature from 1 to 2. Okay, the fuel will absorb the heat from this hot air, and there will be a combustion. Okay, and then the working fluid or the mixture of fuel and air will go to the turbine and will produce a work net, and the exhaust gases will go out, and the cycle will repeat again. But they are not connected. The exhaust gases went out, and you will have a new fresh air. Okay, this we call it open cycle. Okay, because the working fluid or the mass flow rate will not complete a closed cycle. Like here, when you have there is no exhaust or intake, like our assumption for idle diesel, Dole, and Otto cycle, that we remove the intake and exhaust valves. Okay, here also we will replace the combustion chamber by a heat exchanger. Okay, instead of increasing the temperature from 2 to 3 because the combustion inside the combustion chamber, we will add a QN. Okay, and this QN will heat the working fluid from 2 to 3. And in our ideal Brayton cycle, we assume there is only air. The air standard assumption is assume that we have only air, so there will be no fuel. The working fluid will be only air. Okay, and then the temperature will increase from 2 to 3 and will go to the turbine. And now we will not have an exhaust gases. The exhaust gases have a high temperature. Okay, at state 4. More than at state 1 when you take the air, fresh air. So the temperature is decreasing from 4 to 1. Okay, it's decreasing from 4 to 1. And to replace this, the actual or the open cycle here, we will put also a heat exchanger, but with a Q out or heat rejection. So by decreasing or taking out a heat, the temperature will decrease from 4 to 1. And that is a closed cycle because the mass flow rate or the working fluid will complete a complete cycle. It will start from 1 and will go again to 1. Okay, that is the difference between open cycle and closed cycle. And what we have done in auto, diesel, and dual cycle, that we have a closed cycle. The mass flow rate will complete a closed cycle. Okay. Regarding also the pressure ratio, by increasing the pressure ratio, the thermal efficiency of Brayton cycle will increase. Okay. And we have an equation for the thermal efficiency exactly under only cold air standard assumption. We will not have this equation in the variable specific heats. Okay, that the thermal efficiency is a function of the pressure ratio. Okay, so we can calculate the thermal efficiency directly from here. We have that K is equal to 1.4. Okay. So by increasing the pressure ratio, this term will decrease, and the whole term for the thermal efficiency Brayton will increase. So the thermal efficiency for Brayton cycle is increasing by increasing the pressure ratio. Also, regarding the pressure ratio, work for fixed values of T minimum and T max. T minimum is at state 1. Okay, here you can see that T minimum is at state 1. That is T1, and T maximum is T3. Okay, for fixed limits or fixed values of T minimum and T maximum, the network of the Brayton cycle first increases with the pressure ratio, then reaches a maximum at RB equal to T max over T minimum. This also can be represented as RB equal to T3 over T1 power K over T2K minus 1. Okay, this equation can be written also here, this one, T3 over T4S. Okay, we can say that okay, we can, it is T3 over T1, so it is not related. Okay, but this equation represents how the pressure ratio and when the work will reach its maximum. Here, this graph represents that we have T maximum, the maximum limit, T, which is equal to T3, and T minimum, T1. Okay, by increasing the pressure ratio, what is the meaning of pressure ratio? Means this line represents the B1 or B1 equal to B4, and this line, okay, will equal to B2 and equal to B3. Okay, so if I have B2 and B3 is here, okay, it's like this. Okay, it's like this. Then the area enclosed inside the TS diagram is equal to Q in Qnet, okay, Qnet, and Qnet is equal to Wnet. Okay, so as you can see, it is a very small area. So by increasing the B2 equal to B3, we are increasing also the area. So by reaching a maximum B2 equal to B3, when we touch this line, the maximum pressure line, okay, the maximum temperature line, sorry, okay, we will have the maximum pressure, okay. So that is for RB equal to 2. Okay, then when you go up again, it will this one is maximum, then and finally it decreases. I don't know, I don't understand what is the meaning of finally it will decreases. Okay, and this also can happen here for pressure ratio equal to 8.2. So this one is the line for pressure ratio 8.2. Here, if we have B2 equal to B3 like here, it will be the work net will be minimum. But by increasing the pressure line until we reach the pressure ratio of 8.2, we'll have work net maximum. Okay, that is the meaning of this figure. Also, for the turbine and compressor, as you can see, they are on the same shaft. Okay, so the work turbine يعني the turbine is a producing device, okay, work producing device. It will provide us with W net, but this W net is equal to the turbine, the work turbine minus the compressor turbine. So we can say that the work turbine is not the whole work of the turbine is not converted, all of it, to be work net. Some part of this work turbine is used to derive the compressor, okay. The fraction of the turbine work used to derive the compressor is called the back work ratio, okay. So the back work ratio, we represent it like RBW, okay. It is the ratio between the work of the compressor and the work of the turbine. So it is equal to work in over work out, or the work of the compressor of the work of the turbine. And I put S for each one because it is ideal Brayton cycle يعني. Under S is constant isentropic process, there is no heat addition, and also it is internally reversible process يعني. Okay, because usually you will have actual cycle in Brayton cycle questions. Okay, so returning back to our question, air passes through the engine at a rate of 1 kilogram per second. So we have m dot, and it is m dot s because it is ideal cycle, خلاص, 1 kilogram per second, and the air at the beginning of the compression is at 70 kilopascal. So the beginning of the compression process, this is the isentropic compression process from 1 to 2. Here is the compressor, okay, here is the compressor from 1 to 2. So at the beginning means B1, okay, B1 is equal to 70 kilopascal, and T1 is equal to 0 degrees Celsius and equal to 273 Kelvin. Determine the power produced by this engine. Okay, power means W net dot, okay, because it is power rate. So we need to find W dot net. And the thermal efficiency, and it is the thermal efficiency of the ideal Brayton cycle. We have ideal cycle, okay, and use constant specific heat at room temperature. Constant specific heat at room temperature is 300 Kelvin. So table A to A, يعني table A to A. In this cycles, we are not using the average CV or CB. We're using CV and CBK, the specific heat ratio under a temperature of 300 Kelvin, the room temperature, okay? So use constant specific heat, and we will solve this question also in variable specific heat. So these are the two requirements. How can I find W dot net? This is the equation sheet for ideal Brayton cycle under constant specific heat, or cold air standard assumptions. W dot net can be found here, okay. I have the mass flow rate. I want W dot net, okay. You can use also that W dot net over Q dot N and find I have Q dot N, but I don't have the thermal efficiency. It is also required. That is why I cannot use this equation to find W dot net. But I have that W dot net is equal to M dot S times W net S in small kilojoule per kilogram. I have M dot S. I want to find W dot net, but I don't have W net S. W net S, as we said, that it is the work out from the turbine minus the work in of the compressor, and can be equal to QNS minus Q out S, which is Q net, okay. S, okay, because it is ideal cycle. So we can solve for W net using two equations. Either you say W out minus WNS and or QNS minus Q out S. So let's solve with these two equations and see if they will give us the same numbers. Okay, for the work turbine out, this is the equation, CB T3 minus T4S. So we have that work out S is equal to CB T3 minus T4S. CB from the table A to A is 0.7, okay, CB is 1.005 and CV is 0.718. So we need CV 1.005, okay. I have CB, CB, but I don't have T3, it is not given in the question, and I also don't have T4S. Okay, so how can I find T3 and T4S? And it is obvious that we cannot find them because the work turbine out is here, okay, W out is. And we need to solve first for the beginning states. We need to solve first for T1. T1 is given, so we need to find T2. Then we can find states, the properties at states 3 and 4. So we cannot solve for the work turbine first, but let's see how can we find T3. T3, as you can see, it is here in this equation. I have RB, okay, I can say that RB, I have it, K1 is equal to 1.4, but I need T4S, okay, that is the problem, that I don't have T4S and I don't have T3, so I cannot use this equation because I have two unknowns. Okay, so let's see for the second one. I can't find W out S, so what about WNS? Let's see how can I find it. Okay, so WNS is equal to CB T2S minus T1. I have T1 given the question. CB is 1.005 kilojoule per kilogram Kelvin. What about T2S? T2S can be found from this equation. Taking T2S over T1 is equal to RB power K minus 1 over K. So let's find that T2S over T1 is equal to RB over K power K minus 1 over K. Okay, so why I'm saying it is S, everything is S, because when we have actual cycle, we will not have isentropic compression process or isentropic expansion process. The compression process will take a path like this, a process like this, and here this one will be T2 temperature to T2A, okay, at or state 2A. Usually we in idle cycling we call it 2, but when we have actual cycle we needed to say to put a subscript 2S, okay. That's why from the beginning I said خلاص, let's put it always S for the ideal cycle, and here also at state 4 it will be 4A. Always you go to the right. If you have a compression you will go up and to the right, and if you have an expansion in the turbine you will go down and also to the right, okay. As you can see, 1 and 3 are fixed. They don't have a subscript S or A, so they are the same. The properties are the same for the actual and ideal cycle at state 1 and 3, but they will be different at state 2 and 4. So this states that we want to find when we have actual cycles. Okay, so for this one, T2S then equal to T1 RB power K minus 1 over K. T1 is 273, RB is 10, power 1.4 minus 1 over 1.4, so T2S is equal to 527.08 Kelvin. Okay, then now I can find WNS. WNS, the work N of the compressor, is 1.005 times 527.08 minus 273, and this will equal to 255.35 kilojoule per kilogram. Okay, so we found WNS. So let's try our luck with the other equation to find WNS. How can I find QNS and QOutS? Maybe I can find them directly. So let's start with QNS. QNS can be found easily because I have Q.NS and I also have M.S. So I can divide them, Q.NS over M.S, and find QNS directly. Okay, so QNS is equal to Q.NS over M.S, and will give me that 500 over 1. This one is in kilowatt, but this one is kilogram per second. So this one kilowatt is a kilojoule per second. So second with second. This will give me 500 kilojoule per kilogram per unit mass. Okay. So what about Q out S? Okay. Q out S is equal to CB T4S minus T1. Okay, so CB T4S minus T1. I have T1 given in the question, CB is 1.005, but the problem is the same like what we have in the work turbine out, that I cannot find T4S because already I don't have T3. Okay, so that is the problem. So how can we find the work net S? Actually, you didn't, you still didn't use this equation for Qn. We used this equation directly because we were given the Q dot ns, but we didn't use this equation in QNS. And we calculated T2S, and I have CB, I have QN, which is 500, so I can use it to find T3. Okay, so that is the way of finding T3. Then I can use this equation to find T4S, and now I can find W out S and solve with the equation for the work. And then I can also find for Q out, I will have T4S from this equation. I also can find the work from the equation of the heat, as Q naught S is equal to W naught S. And what I mean by Q net S, Q net S is the area inside enclosed inside the processes of the cycle in the TS diagram, and W net is the area enclosed in the PV diagram. Okay, and they equal to each other. Okay, so let's find or let's use the equation for Qn, that Qns is equal to CB T3 minus T2S. Okay, I have CB, I have T2S, I have QNS, so let's find T3. So it will equal to 500, 500 equal to 1.005. I want to find T3, so yeah, shift solve with the calculator. 527.08. So T3 is equal to 1024.59 Kelvin. And then I can use the equation that T3 over T4S is equal to RP power K minus 1 over K. And then T4S is equal to T3 RP power K minus 1 over K. So T4S is equal to 1024.59 over 10 power 1.4 minus 1 over 1.4. So T4S is equal to 530.68 Kelvin. And now I can find W out S and Q out S. So W out S was CB T3 minus T4S. And now I calculate T4S and I calculate T3. So it is CB 1.005 times T3, which is 1024.59 minus T4S 530.68, and this will give you 496.38 kilojoule per kilogram. And Q out S is equal to CB T4S minus T1. I have T1, the problem was in T4S, so now I found T4S, so 1.005 times T4S, which is 530.68, minus T1, 273, so this will give you 258.97 kilojoule per kilogram. And now I can find W net, okay, using the equation that W net is equal to W out minus Wn, or Qn minus Q out. Okay, so we'll try these two equations. So W net S, using the first equation, which is W out S minus Wns. So W net S will equal to W out S, which is 496.38 minus Wn of the compressor is 255.35, and this will give you 241.03 kilojoule per kilogram. Okay, what about finding also W net S, but using the equation for the heat transfer, Qns minus Q out S, and this will give you W net S is equal to 500 minus 258.97, and it will give you the same number, 241.03. So you are free to use any of these two equations. Okay, and then finally we can find W dot net. okay, because the m dot s is given in the question, and w net s, we calculated w net s, so we can find the power. So w dot net will equal to m dot s times w net s, and w dot net. And usually in w.net in the question, when you have actual cycle, you will not assume it is ideal or equal or actual. You will not put S or A. You can use it with both. Okay. So this one is 1 times 241.03, and will give you also 241.03. But this one is in kilojoule per second. Okay. The second part in this question was to find the thermal efficiency of ideal Brayton cycle. And as you can see, I calculate the Q net S and Qn. I can use this equation, and also I can use this equation in terms of RP. And as you can see that RP is equal to also RP power K minus 1 over K. This term is here in the denominator, so I can replace it also with T2S over T1 or T3 over T4S. I can write the thermal efficiency for Brayton, okay, is equal to 1 minus 1 over T2S over T1, okay, and also it is equal to 1 minus 1 over T3 over T4S, and this will give you that this one will equal to 1 minus T1 over T2S, and this one is also equal to 1 over T4S minus 1 minus T4S over T3. So you can use any one of these 4 equations, okay, so and they will give you the same number. So let's find the thermal efficiency of Brayton cycle, the ideal Brayton cycle, will equal to W net S over Q ns, and will give you 241.03 over 500, and this is equal to 0.482 or 48.2%. And also you can use this equation only in cold air assumption. You can use this equation, and the equation 1 T1 over T2 or 1 minus T4 over T3 only in cold air standard assumption. In variable specific heat, only use this one. Okay, only use this one in variable, but in cold, you can cold air standard assumption specific heat, you can use this equation. Okay, so it is 1 minus 1 RP power K minus 1 over K, and this will equal to 1 minus 1 over 10 power 1.4 minus 1 over 1.4, which is equal to also the same number. And also if you use this equation, 1 minus T4S over T3, which is equal to 1 minus 530.68 over 1024.59. Also it will give you the same number. And also the final one, 1 minus T1 over T2S, will give you 1 minus 273 over 527.08, and this will give you also the same number. And this by this we finished this one is 48.2, okay, 48.2, and by this we finished the question. But what if he asked you about the back work ratio? Back work ratio RBW, it is WN S, and we assume it is the class work because it is ideal cycle, so the back work ratio for the ideal cycle, back work ratio is WNS over W out S. Okay, the fraction of the compressor work over the turbine work. So this one will give you that 255.35 over 496.38, and will give you that the back work ratio is 0.514. Okay. So that is by solving using the constant specific heats. So what about solving using the variable specific heats? So we have the same question again. So let's write the givens. So RB is equal to 10, Q dot NS is equal to 500 kilowatt. We have air, and as usual we treat it as ideal gas. Okay, m dot s ideal cycle, but also only using variable specific heats. Okay, so we have variable specific heats. This one is 1 kilogram per second. B1, which is equal to B4, is equal to 70 kilopascal, and I have T1 is equal to 0 degrees Celsius, and in Kelvin it is 273 Kelvin. Okay, the same thing, I want to find W.net and also the thermal efficiency for ideal Brayton cycle. So the same thing, we want to use this equation. Okay, I have m dot s, but I want to find w net s in order to find the bar. Okay, so w net s is the same also, that is equal to w out s minus w in s and equal to q in s minus q out s. Here the difference that we don't use cb delta t, we have h3 minus h2s and h4s minus h1. Okay, so how can I find, let's start as we did before, the w out s. W out s, and you will not find it because it is at the end at states 3 and 4. Okay, h3 minus h4. You usually start with qn and wn. Okay, so w out s is equal to h3 minus h4s. You don't have h3 and you don't have h4s and you don't have anything at state 3. But you have the pressure at state 4, but you cannot use it because we use table A17 in variable specific heat and it contains no pressure. Okay, also, so we cannot use or we cannot solve for this one. Okay, what about WNS? Okay, the compressor work, it is equal to H2S minus H1. H2S minus H1. I can find H1 because I have the temperature at state 1, so I can say that T1 can, which is equal to 273, can be used to find H1 using table A17. Okay, and what about H2S? H2S, I need a property as state 2, so I can find H2S from table A17. In diesel, Dole, Otto, and Otto cycle, we use the relative volume, but here in Brayton cycle, we use the relative pressure. Okay, so if I want to find H2S, okay, I need a property at state 2, which is the relative pressure at state 2. I have the pressure ratio given in the question, but the problem is that I don't have PR1 in order to find PR2. So also I will use T1 to find PR1. Okay, find PR1, and from PR1 I can use the equation that RB is equal to PR2 over PR1, and then I can find PR2, and from PR2 using table A17, I can find H2S. Okay, so then I can find WNS. So what about QNS? Okay, we will solve later because if you want to, we finish the question just in like this, in this timeline. Then you can go for the other videos because there will be a lot of interpolation. Okay, for QNS, if I want to solve using this equation, QNS is equal to what? H3 minus H2S. But I already can find QNS because I have Q dot NS, and I can use this equation, Q dot NS over M dot S. I can find QNS. So the same like what we did in the constant specific heat. So QNS equal to Q dot NS over M dot S, and will equal to 500 over 1, and equal also 500, but in kilojoule per kilogram. The problem that when I go to Q out 4, Q out S, is equal to H4S minus H1. As you can see here, that Q out S is equal to H4S minus H1. H1 can be found, or I already found it using T1, okay, from table A17, but the problem is in H4S. In H4S, I need a property at state 4, which is the relative pressure at PR4, but the problem that I don't have PR3 in order to use RB and PR3 to find PR4. So if I have a property at state 3 first, I can find BR3. Then I can use this equation to find BR4, and then I will go to H4S. But the problem that I don't have a property at state 3. T3 is not given in the question. Even H3, I didn't find it. So I need to find H3, and the problem that I don't have anything, but I can use the equation for the QNS as we did in the constant specific heat. We used QNS is equal to CB delta T, and we found T3. Here we will find H3. Okay, so I will use this equation that QNS is equal to H3 minus H2S. Okay, I have Q and S. I will calculate H2S from here. The problem is that I want to find H3. So H3 will equal to Q and S plus H2S. Okay. Q and S is 500. H2S I will find it. Then using H3, I will go to the table. Okay, to find BR3 from table A17. And after this, I will use the equation RB is equal to BR3 over BR4 in order to find BR4. And then I will use again this BR4 from table A17 to find H4S, and then I can find Q out S. And by this, and by this, I can find the W net. Okay, because also I can find it from here, from W out minus W in. I already calculated H3 from this equation, H4S from the table. So let's see how can we solve for this question. Also, if he asks you about the back work ratio, it is equal to WNS over W out S. Okay, so let's find what we want to find. Okay, if you understand the idea, just go to the next video about actual Brayton cycle. Okay, so T1 is equal to 173 Kelvin, and I want to find what H1 and PR1. Okay, at 273, I will go to table A17 for air. So 273 is between these two numbers, so I need to do interpolation. Okay, so let's do interpolation in order to find H and BR. So between T, H and BR. So T is 270, T1 is 273, 280, H will be 270.11, H1. I want to find H1, 280.13, PR is 0.9590, PR1, and here is 1.0889. So 273 minus 270 over 280 minus 270 equal to H1 minus 270.11, 280.13 minus 270.11 will equal to PR1 minus 0.9590 over 1.0889 minus 0.9590, and this will give us that H1 is equal to 273.116 kilojoule per kilogram, and PR1 it is a dimensionless quantity, is equal to 0.99797. Okay, so now I can use the equation that RB is equal to BR2 over BR1 in order to find BR2, and then find using the table H2S. So BR2 will equal to RB PR1, and then BR2 is equal to 10, which is RB given the question, times 0.99797, and this will give you that RB or BR2 is equal to 9.98. And then I will use this value for BR2, 9.98, which is between these two numbers, in order to find H2S in the column of H. Okay, so I need to make another interpolation between H and BR. So it is 523.63 H2S over 533.98, 9.684 over 9.98, 10.37. So H2S minus 523.63 over 533.98 minus 523.63 is equal to 9.98 minus 9.684, 10.37 minus 9.684. So H2S will equal to 5 to 8.1 kilojoule per kilogram. And now I can find H3 using the equation of the Qn. H3 is equal to Qns plus H2S. Qns is 500 and H2S is 528.1. So H3 will equal to 1028.1 kilojoule per kilogram. Okay, now I found H3. I want to find H3 because then I will use it to find PR3, then find PR4 in order to find H4S. Okay, so the next step is to find PR3. Okay, so I will go to the table with this value of H3, 1028. Here is the column for H. 1028 is between these two numbers, so I want to find PR, so I will make interpolation between these two columns. Okay, so H PR 523 1023.25, 1028.1, which is H3, and 1046.04, and the corresponding values for PR is 105.2. I want to find PR3 and 114.0. So by making the interpolation, 1028.1 minus 1023.25 over 1046.04 minus 1023.25, and this will give you that PR3 minus 105.2 over 114 minus 105.2 will give you that PR3 is equal to 107.073. So RB is equal to PR3 over PR4, and then PR4 is equal to PR3 over RB. So PR4 is equal to 107.073 over RB, which is 10, and this will give you PR4 is equal to 10.773 dimensional this quantity. So now I will take PR4 again and go to table A17. It is 10.773. So PR 10.773. 10.773 is between these two numbers. Okay, and I want to find H4. So I make interpolation. So it will be like this. H PR. H is 533.98. I want to find H4S 544.35. PR is 10.37. This one is 10.773. 11.10. So H4S minus 533.98 over 544.35 minus 533.98 will equal to 10.773 minus 10.37, 11.1 minus 10.37. and this will give you that H4S is equal to 539.7 kilojoule per kilogram. Then finally, you can find W out S, W in S, Q in S. So W out S is equal to H3 minus H4S, and will give you that it's equal to 1028.1 minus 539.7, and this will give you 488.4 kilojoule per kilogram. WNS is equal to H2S minus H1 and equal to 528.1 minus 273.116, and this will give you 254.984 kilojoule per kilogram. And for we know that QNS is equal to 500 kilojoule per second, and we wanted to find Q out S. Okay, so Q out S is H4S minus H1. So Q out S is equal to 539.7 minus H1, 273.116. So Q out S is equal to 266.584 kilojoule per kilogram. And now I can find W net S using these two equations, that W net S is equal to W out S minus WNS of the compressor. So 488.4 minus 254.984 will give you that W net S is equal to 233.416 kilojoule per kilogram. And if I use the other equation, W net S is equal to QNS minus Q out S is equal to 500 minus 266.584, and it will also give you the same number, 233.416 kilojoule per kilogram. So use any of these two equations. For the thermal efficiency of Brayton cycle, you can only use this equation, that W net S over QNS is equal to 233.416 over QNS, which is equal to 500. So the thermal efficiency will equal to 0.467 or 46.7%. As you can see, this one is 46.7%. When we found the efficiency for the closed one, it was 0.482. So in cold air standard assumption, it is predicted that the thermal efficiency will be higher than the variable specific heats assumption, because the variable specific heats is more accurate, but the constant specific heat has an error in positive. Okay, so if he asked you about the back work ratio, okay, it will be equal to WNS over W out S. So WNS is 254.984 and W out S is 488.4. So it is equal to 0.522. Okay. So and as you can see also, this one now is higher than the one in the constant specific heat, because what is the meaning of back work ratio? It is better for me to increase it or to decrease it. The better for me is to decrease it, because it is a ratio between work in over work out. If it increase, that means that the work in is higher, is more, you are taking a big part from the work of the turbine, and in order to make the compressor work. Okay, so by increasing this one, it is a bad thing for me, because it is a consuming device, and by increasing this one will increase. Okay, and this is a bad thing for me. So that is why for the cold air standard assumption, it is showing to you it is everything is very good, and that is why that back work ratio is less. But here the realistic one, or the accurate one, is 0.522. So it is worse for me to have a backwork ratio 0.522, which is higher than the backwork ratio from the cold air standard assumption, but that is the accurate one. Okay, so it is better to decrease the backwork ratio. Okay, so that is for this video, inshallah, and in the next video we will solve about the actual Brayton cycle, and usually the questions will be about the actual Brayton cycle. Okay.